Hello and welcome to our Wednesday webinar from the International Center for Sustainable Carbon. My name is Benedicta and I'm part of the communications team here. Our monthly webinars are based on our technical reports, which are available from our website, sustainable-carbon.org. Please type in any questions you may have in the questions box as we go along, and we'll answer them at the end of the webinar. The subject for today's webinar is prospects for reduced emissions using clean ammonia, presented by Dr. Qian Zhu. Over to you, Qian.
Thank you, Benedicta, for the introduction. And welcome everyone to today's webinar. In the next 30 minutes or so, I will discuss the prospect for reduced emissions using clean ammonia as a fuel. And here is today's outline. Firstly, I will describe briefly the various material technologies available for the commercial production of clean ammonia and compare the carbon footprints and the costs of ammonia from different production methods. I will then discuss the ammonia fuel use and the ammonia combustion technology development for power generation and shipping, as well as its potential to decarbonizing these sectors. I will also review the latest developments in production and the utilization of ammonia fuel, and finally, the key messages from this study. So if you have any questions, please put it in the question box and I will try to answer them at the end of the presentation. Firstly, let me clarify the definitions of different types of ammonia used in this study. The ammonia made using unabated fossil fuel, such as natural gas and coal, as the feedstock, is referred to as unabated ammonia. Low carbon ammonia is ammonia produced using fossil fuels as feedstock, combined with carbon capture, utilization and storage, in short, CCUS, to reduce its carbon footprint. Renewable ammonia is produced using using water and air as feedstock, with the entire process being powered by renewable energy. Both renewable and low carbon ammonia are regarded as clean ammonia. There are three established technology pathways to produce clean ammonia at industrial scale. They are natural gas reforming and coal gasification integrated with CCUS, and the water electrolysis for hydrogen production, followed by the Haber-Bosch process to convert hydrogen and ammonia and nitrogen into ammonia. When renewable electricity is used, water electrolysis-based HB process produce renewable renewable ammonia, and no CO2 is emitted from the production process. Alkaline electrolyzers and proton exchange membranes, or PEM electrolyzers, are currently used in commercial production of renewable hydrogen. Solid oxide electrolysis cells, SOEC, are an emerging technology for hydrogen production that have higher energy efficiency. Currently, the production of ammonia relies heavily on the use of unabated fossil fuels, both as a feedstock and as an energy source. For ammonia to play a critical role in a clean energy transition, the production of ammonia must be decarbonised. Over 60% of the total CO2 produced during fossil-based ammonia production is processed CO2, which is a stream of pure CO2 ready to be transported, used, or permanently stored. The remaining CO2 emissions occur when fossil fuel is burnt to generate heat, steam, and electricity required by the process. This CO2, which is about 1/3 of the total, should also be captured and removed. Carbon capture technologies for emissions reduction of flue gases from fossil fuel combustion are commercially available and are proven at industrial scale. Some new technologies are emerging. For example, the autothermal reforming for natural gas-based hydrogen production has gained popularity due to its potential for a higher CO2 capture rate. And it has been selected in several projects under development for low carbon hydrogen or ammonia production. Another example is the actual low carbon hydrogen and ammonia production process developed by 8 Rivers Capital. It uses oxy-combustion and pressurized CO2 in a CO2 convective reformer, resulting in over 99% of CO2 removal rate. A commercial ammonia production project using this technology is currently under development in Texas, USA. The carbon footprint of ammonia production depends on the production method used and the plant efficiency. While modern, efficient, unabated gas-fed ammonia production may have a carbon footprint of 1.6 tons of CO2 per ton of ammonia produced, the average unabated European ammonia production plant in 2020 typically emitted approximately 2 tons of CO2 per ton of ammonia. For unabated coal-based ammonia plant, emission intensity can be 3 tons CO2 per ton of ammonia. CO2 emissions from fossil-based ammonia production can be reduced by over 90% when carbon capture is added. This slide compares the life cycle greenhouse gas emissions of ammonia produced using different methods. And you can see that carbon intensities of clean ammonia are much lower than unabated ammonia. Today, the cost of renewable ammonia is about 2 to 3 times higher than unabated ammonia, which is a major obstacle to its large-scale deployment. Low carbon ammonia is also more expensive than unabated ammonia, but it is much cheaper than renewable ammonia. Under right conditions, low carbon ammonia can become competitive with unabated ammonia. Therefore, low carbon ammonia can be a viable choice as a clean fuel for an immediate and a cheaper start to large-scale decarbonization of hard-to-abate sectors, bridging the transition towards renewable ammonia fuel use in the longer term. This slide shows the current and the future costs of ammonia from different production methods between 2020 and 2050, projected by researchers at Carbon Direct. Ammonia co-firing is promoted as a technology for decarbonization of coal power generation, mainly across Eastern and Southern Asia, where electricity production is dependent on coal. In particular, Japan and South Korea have set ambitious targets and published roadmaps for research, development, and the deployment of ammonia fuel for power and shipping sectors. Japan aims to co-fire 20% ammonia at its coal power plants by 2030 and expect to import 3 million tons per year of clean ammonia then. South Korea aims to commercializing ammonia coal co-firing from 2027 and burn 20% ammonia at more than half of its coal power stations from 2030. And this will generate a demand of around 3.8 million tons ammonia annually. Other countries, including Indonesia, Singapore, Thailand, the Philippines, Malaysia, and India, also encourages the deployment of ammonia firing and the co-firing technology for power generation. Active research and development of ammonia firing or co-firing in thermal power generating units are being carried out, and the progress has been made. Japan's utility JERA has just concluded a 3-month demonstration testing of co-firing 20% ammonia with coal at a commercial 1,000 megawatts coal power unit in Japan. Test results confirm that stable combustion could be achieved with complete combustion of ammonia. NOx levels from ammonia coal co-firing were no higher than when firing coal alone. So it can meet the NOx emission can meet stringent emission standards. Sulfur oxide emissions were reduced by 20%, and the generation of nitrous oxide was below the detection threshold. Similar results have also been reported in China, where ammonia co-firing at a ammonia coal ratio of up to 35% have been demonstrated successfully at existing 500 and 600 megawatts unit. This has a great significance to decarbonization of coal power generation in China, as units with a capacity of 600 megawatts or larger accounts for over 60% of China's installed thermal power capacity. China now plans to demonstrate co-firing over 50% ammonia with coal at a 1,000 megawatts coal power unit. Technologies for ammonia coal co-firing in pulverized coal and Circulating fluidized bed boilers are also under development in other countries, such as South Korea. Efforts are continuing to increase the ammonia co-firing ratio to 50% and eventually to 100%. Based on the positive results, Japan's JERA will begin construction soon to enable commercial operation of 20% ammonia coal co-firing at its Qian power station, and hope to establish technologies for wider use of ammonia as fuel in thermal power generation by March 2025. Research and development is also ongoing, which demonstrates the feasibility of ammonia direct firing and co-firing in gas turbines. Test results show that gas turbines can fire 100% liquid ammonia with minimal emissions of nitrous oxide. NOx emissions can be lowered to the required levels by combining a HPR unit with a purposely designed two-stage low NOx ammonia combustor, like this one showing here. So this indicates that ammonia has the potential to be used in a gas turbine combined cycle GTCC power plant. And this slide shows a conceptual design of an ammonia-fueled GTCC power plant using a H25 gas turbine and a two-stage combustor. The developers aim to commercialize ammonia-dedicated gas turbines by 2025. So it can be expected that there will be initial technology demonstrations of ammonia firing and co-firing at various types of commercial coal and gas-fired power plants around 2025, followed by large-scale implementations closer to 2030. Fuel cells can be used for off-grid applications, such as telecommunication towers, and in remote locations that lack grid access or where the grid is unstable and the backup power is frequently required. Ammonia can be used directly in direct ammonia fuel cells or indirectly with ammonia being reformed into hydrogen and nitrogen before hydrogen is fed into the fuel cells. The direct ammonia fuel cells under investigation are mainly the SOEC type. Indirect ammonia fueled fuel cells are also under development and are emerging into the commercial market. The estimated life cycle greenhouse gas emissions of fossil fuels and clean ammonia are compared in this table here. As you can see that both renewable and low carbon ammonia have life cycle greenhouse gas emissions significantly lower than coal and natural gas. Therefore, replacing fossil fuels with clean ammonia can reduce carbon emissions from power sector. It is estimated that 50% ammonia coal co-firing could reduce the total greenhouse gas emissions from global coal power generation by 43.5 to 49.5%. Replacing 100% natural gas with clean ammonia fuel could lead to greenhouse gas emission reductions ranging from 39.4 to up to 96.3. Furthermore, analysis show that ammonia firing and co-firing with fossil fuels at power plants can be a cost-effective decarbonisation solution, and it's easy to implement in the short term. As around 95% of all freight transport taking place at sea, consuming around 10% of global transport energy and accounting for 2.6% of greenhouse gas emissions, the shipping industry faces a substantial challenge to decarbonize its operations. The International Maritime Organization, IMO, set new emissions reduction targets in July 2023 to reduce CO2 emissions by at least 40% from the 2008 level by 2030 to peak greenhouse gas emissions from international shipping as soon as possible and reaching net zero emissions by or around 2050. The revised IMO greenhouse gas strategy also includes ambitions of uptaking net zero emission on near net zero emission technologies, fuels, and/or energy sources to represent at least 5% and aiming for 10% of the energy used by international shipping by 2030. Several regional and national governments have also set ambitious emission reduction targets for the shipping sector. Ammonia is a promising alternative marine fuel that has various advantages over other alternative fuels. These include an existing logistical infrastructure with no need for cryogenic storage. The ammonia has a higher energy density in liquid form than some other clean fuels, enabling voyages of some weeks. The properties of ammonia and other existing and potential marine fuels are compared in the table on the left. The combustion characteristics of ammonia do not prohibit its use as a fuel, and the existing technology can deliver commercial performance within regulatory limits for emissions of NOx and nitrous oxide. Ammonia-fueled two-stroke and four-stroke engines for both new builds and the retrofits, as well as the ammonia-fed fuel cell-powered vessels, are being developed by major maritime engine manufacturers. The first commercial ammonia-fueled vessels are expected to be operating at sea by 2024-2025. More widespread adoption is anticipated in the following years. The figure on the right here shows the annual number of ship technology projects under development in recent years by fuel focus. It demonstrates that the new conceptual shipping fuel projects have been increasingly focused on hydrogen and ammonia fuels. Also, Many shipping companies plan to retrofit their existing vessels to run on ammonia fuel. The 2023 Net Zero Roadmap by the International Energy Agency considers that it will be ammonia, not methanol, that should emerge as the key shipping fuel and play a major part in decarbonizing the global shipping industry. The figure on the right here compares the life cycle greenhouse gas emissions of ammonia relative to very low sulfur fuel oil. The figure on the left compares the life cycle greenhouse gas emissions of alternative marine fuels. Well-to-tank emissions represent the upstream emissions from the fuel production and the transport distribution. The tank-to-wake emission are emissions from fuel use on board, which is fuel combustion from fuel combustion. And you can see that clean ammonia has life cycle greenhouse gas emissions much lower than fossil fuel and most other carbon-based alternative marine fuels. The results from several analyses all indicate that replacing fossil oil with clean ammonia fuel could reduce carbon emissions from shipping vessels by up to around 90%. Studies also found that new build and retrofitted ammonia-fueled ships can operate at lower costs than conventional heavy fuel oil ships with substantial emission reductions. The clean ammonia is gaining attention commercially and from policymakers. Momentum is gathering in building a clean ammonia value chain. A number of clean ammonia production projects have been announced across the world, as shown in this slide here. The bubble size indicates the production capacity of the announced project. Some projects are in advanced development stages of either under construction or reaching a final investment decision. The majority of the projects are for renewable ammonia production. As you can see, Australia is the most active region for clean ammonia production. Several mega-scale projects are also under development in regions including the Middle East, Africa, and North America. The majority of global low-carbon ammonia production capacity could possibly be in the USA, where the plant, ACE plant, has a capacity, ammonia production capacity of 7.2 million tons ammonia per year. It will be the world's biggest low-carbon ammonia production plant once operational in 2027. In addition, significantly greater plant production capacity is targeted for more novel applications such as fuel and energy than for fertilizer production. There are multiple initiatives to explore ammonia fuel use for shipping. As part of achieving the IMO's net zero emission target and to help overcome barriers to the uptake of clean fuels and technologies for shipping. The establishment of green shipping corridors was initiated at COP26 in 2021. Since then, more than 50 green shipping corridor initiatives have been announced. A green shipping corridor is a route between two or more ports where zero-emission shipping solutions are demonstrated and reported. Ammonia-fueled two-stroke and four-stroke engines, as well as ammonia-fed fuel cell-powered vessels, are under development. At the start of 2024, there are 579 ships, either on order or in operation, with dual fuel-ready status, in which 322 are ammonia-ready. Meanwhile, retrofitting existing vessels to run on ammonia fuel are on the way in regions including Europe and USA. The first demonstration will begin as early as 2024. As mentioned earlier, Japan is progressing in developing and deploying ammonia combustion technologies for power generation. There are also active collaborations between technology providers, utility companies, and other industrial players to develop and implement clean ammonia fuel use in coal and gas-fired power generating units in other countries. Several feasibility studies have been launched to explore the possibility of ammonia direct firing or co-firing for power generation, mostly in Asia, but also in South America and Europe. As an example, Japan's MHI and South Korea's Doosan and Ability are working with Indonesia Power on co-firing ammonia and Java 9 and 10 unit. Java 9 and 10 are two 1,000 megawatt coal power generating units under construction as the expansion of the existing Suralaya power station in Indonesia. They are expected to begin operation in 2025. The two units will be the first ultra supercritical coal power generating units in Indonesia, and the only ones equipped with HCR for NOx control. Co-firing up to 60% ammonia at the units are planned for 2027. Ammonia co-firing was tested at Unit 1 of the power plant in September 2023. Elsewhere, a 60 megawatt, 100% ammonia-fired GTCC power plant is planned to be built in Singapore, and another ammonia-fired GTCC plant in Ireland is proposed. Ammonia firing and co-firing have also been demonstrated successfully in industrial processes such as cement and ceramic making and steel processing. So the key messages: utilization of clean ammonia as a fuel provides viable pathways to decarbonize several industries, including power generation and the maritime shipping. various well-known, well-proven mature technologies are available for the commercial production of clean ammonia. New technologies are emerging that can produce ammonia with even lower carbon footprint. Both renewable and low-carbon ammonia have life cycle greenhouse gas emissions markedly lower than fossil fuels, and therefore can make a credible contribution to the long-term decarbonization of power and shipping sector. Ammonia combustion technologies for applications in coal and gas-fired power generation, maritime shipping, and industrial processes are advancing rapidly. Commercial demonstrations are expected from 2024-2025, followed by large-scale implementation afterwards. Thank you for your attention. And let's see if there are questions. Yeah, there are some questions here. The first one, renewable electricity is cheaper than fossil-generated electricity now. Why decarbonize power sector using ammonia fuel, which is even more expensive? Well, there are countries that are dependent on coal to provide secure, reliable, and affordable energy and power. Some of the countries have a young coal fleet. For this country, coal power plants will continue operating for at least 20 years or more, and therefore needs to find ways to decarbonize the coal power generation. Of course, CCUS is one option. However, some plants may not have easy access to storage sites, nor off-takers nearby for the captured CO2. Or some plants are towards the end of their service life, so the CCS is not a viable choice because operators are unlikely to get return on investment with the limited remaining life. So in these cases, ammonia firing or coal firing can provide a decarbonization solution. And even for countries that are progressing well in developing renewable energy and in clean energy transition, thermal power plants will still be required for next decade or more to support the grid. Burning ammonia instead of fossil fuel, such as natural gas, in these thermal power plants, again, provide a pathway for low carbon electricity generation. For example, Japan has received criticism for its approach of ammonia co-firing to decarbonize its power generation. But Japan is in the unique situation here. It is an island country with no grid connection to neighboring countries. And Japan has limited energy resources, so it has to rely on imports for almost all its oil, natural gas, and coal supply. Japan diverses its energy supply in order for safety and energy security. Japan also has limited renewable energy resources, so it has to take a different approach to decarbonizing its power sector and other industries to achieve its net zero emission goal. Clean hydrogen and ammonia could form the basis of an integrated clean energy supply, storage, and distribution solution. Japan has been actively working with other countries such as Australia, the countries in the Middle East, to establish supply chain of clean hydrogen and ammonia for use as fuels in Japan. So there is a prospect of clean ammonia fuel use for decarbonization of power, transport, and other industrial sectors. Next question. If you want to use natural gas to make low carbon electricity by deploying CCUS, why should you not just simply burn the natural gas in the gas turbine and capture CO2 produced? Do you gain any real advantage if instead you make ammonia from natural gas and burn that? Yeah, I showed in this presentation, the life cycle carbon emissions are lower from ammonia, from clean ammonia than from the natural gas. So if you have to carry on generating electricity using thermal power plants, then displacing ammonia with displacing the natural gas with clean ammonia can decarbonize, lower the carbon emissions from power generation, and for countries to rely on thermal power generation and also to achieve net zero emissions, the ammonia is a viable provide a pathway for low emission power generation. And that's it. No more questions.
Great. Thank you so much, Qian. All that's left for us to say really is the slides from this webinar will be available to download from the webinar page shortly. And the report on this subject should be out by late summer. Thank you to all of you for joining us today, and goodbye.